Hey there. Tonight, we are slipping back into a world so old, it almost feels impolite to call it Earth, because the place would hardly recognize its modern name. Recently, researchers fed geochemical records, ancient zircon data, fossil chemistry, and climate models into advanced AI systems trained to compare billions of years of planetary change. And what came back was not the picture of a dull, empty age, but a restless, half-made world, dimmer under a younger sun, breathing poisonous air, holding red metallic seas, and quietly preparing every condition that would one day make forests, animals, and people possible. So if that sounds like your kind of late-night trouble, the slow, ancient kind, then do me a small favor and like the video. Maybe subscribe too, and then let your shoulders drop a little. Let the room go softer around you. Let your jaw unclench. Breathe in slowly. Breathe out even more slowly. We have no appointments in the Proterozoic. No emails. No traffic. Just deep time, bare stone, and more years than the mind really knows what to do with. If you were standing here with me at the opening of this eon, you would not see a world that felt welcoming. You would see age? Certainly. The Earth was already old, more than 2 billion years old, which is a wonderfully humbling thought if you have ever felt tired on a Monday. This planet had already survived bombardments, volcanic tantrums, continental experiments, and chemical upheavals that make our modern weather look like polite small talk. And yet, despite all that age, the world still felt unfinished. It had oceans. Yes. It had crust. It had drifting continental cores. It had life. But it was life on a scale so tiny, so patient, so invisible, that the whole planet carried the eerie mood of a stage waiting for actors who had not yet learned how to enter. The sun above this old Earth was dimmer than the one that warms your skin now. Not dramatically so in a human sense, but enough to matter. Enough that the planet needed help staying warm. Greenhouse gases did much of that work. Methane, carbon dioxide, water vapor, all of them held heat close, wrapping the planet in a chemically strange blanket. The moon was closer then, tugging more strongly at the oceans. Days were shorter. The rhythm of light and darkness moved to an older clock. Even the spin of the world was still being negotiated. Now picture the continents, or rather, try to picture them and then allow the image to dissolve, because nothing would look familiar for long. There was no North America as you know it, no Africa in its modern outline, no reassuring schoolroom map with neat edges and named oceans. Instead, there were early continental masses, low and stark, gathering and separating under the pressure of plate tectonics already at work. These ancient fragments, the first durable bones of later continents, were forming their cratons, the stubborn hearts of land that would survive unimaginable spans of time. Under modern Canada, under Australia, under Africa, under other continents still recognizable today, the oldest cores were hardening and thickening, preparing to endure. Those cratons were not picturesque places. No soft soil, no moss, no fern, no insect hum, just bare mineral surfaces, volcanic rock, exposed crystalline shields, and rivers cutting across unanchored ground. Without roots to hold anything in place, sediment moved easily. Rain could scour it. Wind could lift it. Everything felt raw, as if the planet had not yet learned the art of finishing its edges. And the oceans. The oceans were stranger still. We tend to imagine ancient seas as simply older versions of our own. Perhaps emptier, perhaps darker, but still blue and breathing beneath the sky in a recognizable way. Not these. The early Proterozoic oceans were anoxic, with little to no free oxygen dissolved in them. Iron floated through the water in abundance, dissolved, mobile, waiting. In some places, the seas may have looked greenish-brown, in others reddish, metallic, faintly ominous, as though the whole planet had steeped itself in a mineral broth. If you dipped your hand into that water, and let us be glad you cannot, it would not feel like a place meant for lungs or gills, or the graceful theatrics of modern marine life. It was a chemist's ocean, a microbial ocean. An ocean that belonged to beings so small the drama of their existence played out molecule by molecule. Life was already there, busy beyond belief. Bacteria and archaea had been experimenting for ages. They thrived in hot vents, in strange chemical gradients, in sediments, in salty shallows, in dark places where sunlight never arrived. They did not need beauty. They did not need scenery. They needed chemistry, and the earth supplied that in abundance. They fed on sulfur, on hydrogen, on iron, on compounds that would make a modern body recoil. They built no shells, left no footprints, sung no songs, and yet they were remaking the entire planet, one invisible reaction at a time. Honestly, I have always found it strange that people call this kind of world empty. Invisible is not empty. Quiet is not empty. A locked room can still be full of plans. The Proterozoic at its beginning was full of plans. If you drifted across one of those ancient shorelines at dawn, and dawn is perhaps the closest word we have, even if nothing about it felt modern, you might see broad flats of wet sediment glazed under weak light. Across them spread microbial mats, thin at first glance, almost like stained skins on the stone. But inside those mats was a layered city. Different microbes occupied different levels according to the chemistry they preferred. Light-loving cells near the top, other organisms below them consuming waste, recycling nutrients, trading compounds like silent merchants in a city with no language and no mercy for inefficiency. Layer on layer, film on film. Life arranged itself into a functioning society long before there were animals clever enough to invent the word society and then make a mess of it. Some of these microbial communities built stromatolites, and if you have never seen one, imagine a dome or column of layered stone rising from the shallows, built not by intention in the architectural sense, but by persistence. Sediment stuck to microbial films. Minerals precipitated. New layers formed. Then more sediment, more mineral, more growth. Slowly, beautifully, absurdly slowly, these structures grew upward and outward. They were among the first visible monuments of life on Earth. Not carved, not cast, grown. The kind of architecture only time could admire. Researchers today have used AI to compare isotopic signatures, sediment layers, and the microscopic textures preserved in ancient rocks. The models cross-reference lab results with known microbial behaviors and modern analogs from places like Shark Bay and hypersaline lagoons. What the systems suggest is that these early communities were not random smears of life. They were structured, stable, ecologically layered systems with clear internal logic, which is another way of saying that even in a world with no animals and no plants, life had already become surprisingly organized. The Earth was not waiting for complexity. It was practicing it in secret. Above all this, the sky remained dangerous. There was no true ozone shield yet, so ultraviolet radiation came down hard. The surface of the planet was bathed in light that could break apart fragile molecules and damage exposed cells. Water acted as a shield. One reason life stayed mostly submerged or embedded in protective mats. The safest places were not the bright open surfaces, but the buffered margins, the shallow water films, the layers beneath layers. Survival often begins in cover. And still, the continents moved. The mantle beneath the crust churned with slow violence. Heat from radioactive decay and the leftover energy of planetary formation drove material upward and downward in cycles too large for any creature to witness, too large even for most rocks to remember cleanly. Granite became more common in the crust. Mineral availability shifted. Elements that would later matter deeply to biology, phosphorus, molybdenum, iron itself, entered cycles that quietly widened the biochemical options available to life. No one was planning for DNA enzymes or metabolic innovation. The Earth was simply rearranging itself, and in doing so, it made future complexity possible. There is a kind of tenderness in that thought. The world was not aiming at us. It was only becoming itself. And in becoming itself, it made room. Somewhere in those shallow waters, under sunlight filtered through murky chemistry, a group of organisms was refining a trick that would change everything. Cyanobacteria, tiny, ancient, blue-green workers of the sea. They were not the first life forms, not by a long shot, but they were among the most consequential. They learned to use sunlight in a way that no one before them had managed so effectively. They split water molecules. They harvested light. They made sugars. And in doing so, they released a waste product into the world. Oxygen. For now, it was only a whisper. A chemical inconvenience. A tiny bubble drifting upward in waters that had no idea what was coming. The planet did not yet know it was about to be poisoned, cooled, rusted, and ultimately transformed by the metabolic leftovers of creatures too small to see. And that, I think, is the perfect Proterozoic joke. The future of the world began not with thunder, not with a giant beast lifting its head, not with a godlike flame splitting the heavens, but with microscopic cells doing chemistry in a puddle and accidentally changing everything. So let the room stay dim. Let the fire crackle softly in your mind. Let your breathing match the old tides of that younger moon, because beneath those metallic waters, among the mats and domes and silent red seas, the long first act of the Proterozoic has only just begun, and the next thing to rise will not be a mountain or a continent. but a dangerous invisible gas that the world has never had to live with before. Before that, rise begins in earnest. Let yourself linger a little longer at the shore, because this is one of those moments in history that deserves to be stretched gently, like warm wax or a final quiet minute before sleep. The stone beneath your feet is dark and cold, not smooth, not comfortable, but pitted, mineral-rich, still carrying the memory of old eruptions. Small rivulets run over it and disappear into shallow pools, the color of weak tea mixed with iron filings. The air tastes faintly of volcanic gas and wet rock. Nothing green softens the horizon. No bird crosses the light. No branch shifts. The only movement is water, a thin wind, and the slow collapse of tiny grains along the shoreline. If you were standing here with me, I think the first thing you would notice would be the silence. The second thing would be that the silence is somehow busy. That busy silence belongs to chemistry. Iron drifting in the sea, carbon moving between air and water, sulfur compounds waiting in sediments, tiny cells multiplying where light reaches them and shrinking back where it does not. You could kneel beside one shallow microbial flat and see almost nothing. Just a glossy skin over mud. Yet if modern instruments were handed their way across that surface, they would detect gradients so fine and crowded it would feel almost theatrical. Oxygen, where it exists, near the top. Sulfide lower down. Zones of photosynthesis. Zones of fermentation. Zones where one community's waste is another community's feast. We think of ecosystems as forests, reefs, savannas, but those ideas are late arrivals. Here the ecosystem is a film on stone, a mat a few fingers thick, a city built from slime and sunlight. In some places, these mats trap enough sediment to begin creating relief. A small rise, then another. Over years, that would mean nothing to us and everything to them. The rise becomes a dome. Silt settles. Microbes bind it. Minerals lock it in. Another layer grows over the top. Time does the rest. By the time a stromatolite stands clear of the waterline at low tide, it has become a kind of biography written in laminae. Each layer says, "We were here. We endured light. We endured burial. We resumed." Scientists still study these structures with a reverence that feels almost personal. AI models now compare the microscopic textures of fossil stromatolites with living microbial communities, not to romanticize them, but to understand the daily logic of their formation. Where the light fell, how sediment pulses changed the shape. When oxygen production spiked, which communities arrived first and which followed after? The result is oddly moving. These ancient forms were not crude beginnings fumbling toward sophistication. They were already sophisticated in ways suited to their time. They were not waiting to become coral reefs. They were being exactly what the Earth needed them to be. And all around them, the sea held its iron. That is important. The iron was not simply present. It was abundant in a way that modern oceans are not. Dissolved, drifting, ready to react. Every future banded iron formation, every ancient mine cut into old rock, every red-black sequence studied by geologists in bright helmets under hard sun. All of that began here, with seas so chemically charged that the arrival of oxygen would act on them like a struck match over dry paper. Not an explosion. More unsettling than that. A slow certainty. The continents, too, were making quiet promises. These early landmasses were low and broad, not yet carrying forests or deserts or the theatrical geography we know today. Yet their cores were strengthening. Cratons thickened and cooled, becoming stable enough to resist later destruction. It is comforting, in a strange way, to know that some stones under our modern feet are direct descendants of that age, survivors from a world no human eye would have endured comfortably. They have outlived oceans, atmospheres, and entire biological eras. They have waded through everything. If rocks can keep secrets, these do. They keep the warmth of a hotter mantle. They keep the memory of an Earth that spun faster, breathed differently, and glowed beneath a dimmer sun. They keep the trace metals that would one day matter to enzymes and cells and metabolisms not yet invented. They keep the quiet record of a planet still assembling itself. And perhaps that is why the beginning of the Proterozoic feels so eerie and so beautiful at once. It is unfinished, yes, but it is not confused. It is preparatory. Like a long inhale before speech. Like a theater before the curtain rises, when the stage hands are still moving unseen in the dark. The creatures doing the work are microscopic. The transformations are invisible. Yet everything essential is underway. Soon, in those shallow waters, Cyanobacteria will keep splitting water and giving off oxygen with the blissful indifference of chemists who do not read the warning labels. Soon the oceans will begin to rust. Soon the air will change. Soon the sky itself will stop being what it was. But for one more moment, the world remains poised, metallic, breathless, waiting at the edge of its first great irreversible turn. The oxygen did not arrive like a hero. It arrived like a mistake that kept repeating. At first, the ancient seas barely noticed. Cyanobacteria in the shallows continued their work with no fanfare at all, turning sunlight into usable energy and releasing oxygen as the extra bit, the chemical scrap left on the workshop floor. Every day, if day is the right word, for a world running on spans too long for memory, tiny bubbles and dissolved traces slipped into surrounding water. And every time they did, the environment pounced. The oxygen reacted immediately with whatever would take it. Iron in the sea, reduced volcanic gases, fresh organic matter. It vanished so efficiently that for a very long while the world could pretend nothing had changed. But change was already there, accumulating like a habit. Imagine the sea floor beneath one of those broad microbial flats. Fine sediment settles. Iron drifts downward through dim water. Above, cyanobacteria release their invisible waste. The oxygen meets dissolved iron and oxidizes it. The iron can no longer remain adrift. It precipitates, tiny particles forming and sinking like rust-colored snow. Layer after layer settles to the seafloor. Then another pulse. Then another. Over spans that make 1,000 human civilizations feel like sparks. These deposits build into banded iron formations, striped records of a planet learning, painfully, how to live with oxygen. Researchers now use AI to compare isotopic fluctuations, mineral textures, and the layering patterns of these formations across Australia, South Africa, Canada, and Brazil. The software is very good at noticing rhythm where the human eye sees only rock. It finds repeating pulses, regional similarities, differences in deposition timing, clues that oxygen production and ocean chemistry were interacting in waves rather than in one simple upward climb. The story that emerges is not neat. It is stop and start, advance and pause. A billion-year argument between life and the chemistry of the planet. And through it all, oxygen keeps being made. Eventually, the sinks begin to fill. The dissolved iron that once swallowed oxygen so greedily starts to thin out. More of it lies buried now, locked into ancient sedimentary bands. Other reactive compounds become less abundant. The sponge, if you like that image, is getting full. Oxygen still disappears quickly, but not quickly enough. A little lingers in shallow water. Then a little more. Then enough to become a problem. That is the awkward thing about oxygen in this story. We inherit it as a blessing, so we imagine it entering the world with trumpets. But for most early life, oxygen was a poison. It damaged proteins. It disrupted enzymes built for an oxygen-free world. It attacked delicate molecular systems that had been evolving comfortably for ages in reducing environments. To them, this was not progress. It was atmospheric vandalism, the great oxygenation event, when it finally gathered enough force to leave a mark in both oceans and air, was less like a sunrise and more like a long chemical siege. Anaerobic microbes retreated where they could, deeper into sediments, into oxygen-poor waters, into isolated niches where the old chemistry still ruled. Some adapted, evolving ways to neutralize oxygen's reactive byproducts. Others likely vanished, erased, with no fossil drama, just fewer cells, fewer metabolisms, fewer descendants. Extinction at the microbial level leaves little spectacle, but it is real all the same. If you were standing with me above one of those shallow Proterozoic lagoons, perhaps on a crust of dark mineral mud, the transformation would still be invisible. That is one of the eerie pleasures of deep time. The biggest revolutions often offer no theater for the eye, no lightning, no collapsing temple, just chemistry crossing a threshold. Still, if we could compress a few million years into a minute and watch from above, perhaps then you would see it. The water changing character, rust spreading through the seas, iron dropping away, surface layers becoming less hostile to oxygen's presence, the atmosphere above losing some of its old haze. That haze matters too. Before oxygen took hold, methane was abundant in the atmosphere, and methane is a marvelous heat trap. It also contributes to hazy chemistry under ultraviolet light, creating airborne particles that may have tinted the sky orange, brown, or amber, something between perpetual dusk and an exhausted sunrise. But oxygen and methane do not coexist peacefully for long. As oxygen increased, methane declined. Molecule by molecule, the atmosphere lost part of its warming blanket, and with that came cooling. The world that cyanobacteria altered with sunlight also became colder because of them. That is the sort of cosmic irony geology specializes in. Small cells, making a little waste gas, accidentally reducing one greenhouse gas and paving the way for massive glaciations. No villain, no mastermind, just feedback loops. The first oxygen lingering in the atmosphere also began doing something else. High above the surface, ultraviolet radiation split oxygen molecules apart. Free oxygen atoms joined other oxygen molecules to form ozone. Slowly, almost shyly, an ozone layer began to emerge in the upper atmosphere. This did not happen overnight, and it did not immediately create a safe, cheerful world. But it mattered. Ozone absorbs harmful ultraviolet radiation. Before it, surface conditions were much harsher for exposed cells and organic molecules. With it, the upper atmosphere began offering protection life had never previously enjoyed. I have always liked that detail. Even while oxygen was poisoning one old world, it was preparing shelter for a future one. The sky itself changed character through all this. You know that feeling when a storm finally passes and the air looks washed, clearer somehow, with edges sharpened by light. The Proterozoic had its own version of that. Those stretched across such absurd lengths of time that no eye could ever have witnessed the whole transition. As methane haze thinned and oxygen increased, the atmosphere became more transparent to the shorter blue wavelengths of light. The old orange murk gave way gradually, unevenly, to something more familiar. Not our modern sky at first, not the full blue confidence of later ages, but a beginning, a clearing, a less alien roof over the world. The rocks remember pieces of this. Red beds, those oxidized sedimentary layers found on continents around the world, record the presence of free oxygen in the atmosphere. Iron in soils and surface sediments reacted with air and turned whole deposits red-brown. These rocks are like the planet blushing after a long fever. They tell us that oxygen had moved beyond the ocean surface and into the weathering world of land. At the same time, life itself began responding in more inventive ways. Some lineages evolved enzymes to cope with reactive oxygen species. Others discovered something even more extraordinary. Instead of treating oxygen only as a threat, they began using it. Aerobic respiration, the process of extracting much more energy from food by using oxygen, started to appear. It was a powerful innovation, but it did not belong to everyone at once. Many microbes remained loyal to the old ways, content in oxygen-free habitats. Yet now the world had options. Oxygen was no longer only an environmental hazard. It was becoming an energy opportunity. Modern researchers studying this transition do not rely on one line of evidence alone. They combine sulfur isotopes, iron chemistry, carbon signatures, sedimentology, and genomic modeling. AI helps by sorting impossible, especially when different continents preserve different fragments of the same planetary shift. What those systems keep confirming is that the great oxygenation event was not a single switch flipped one afternoon by geological fate. It was a prolonged, uneven transformation, full of local differences, stalls, reversals, and overlapping feedbacks. The Earth was not becoming oxygen-rich all at once. It was negotiating with oxygen, sometimes angrily. Meanwhile, down in the seas, stromatolites and microbial mats continued their patient labor. Their layered structures trapped sediment, built domes, and gave shape to coastlines. Shallow water became a place of gradients. Light above, darker chemistry below, oxygen gathering at the top and vanishing with depth. Some parts of the ocean remained stubbornly anoxic for a very long time. Others became stratified, oxygenated near the surface, suffocating below. Sulfur-rich, mid-waters developed in places, filled with hydrogen sulfide and strange microbial communities well suited to that quiet toxicity. The ocean was not one condition. It was many stacked atop one another. There is a scene I keep imagining. A low shoreline somewhere on the edge of an ancient sea. Microbial mats glossy in the weak light. The air cooler now than it once was. A faint metallic smell still present, but different. Less dense. Less ancient somehow. Above, a sky that has begun to clear in patches. Beneath the water, rust falling in invisible drifts. Nothing alive there knows it, but the planet has crossed a threshold it cannot uncross. From now on, oxygen will be part of the story forever. And because the Proterozoic never makes things simple, that threshold comes with new trouble. The breakdown of methane weakens the greenhouse effect. Cooling intensifies. The Earth edges toward its first truly grand glacial catastrophes. The same oxygen that opens doors also closes climates. The same atmosphere that becomes safer for some forms of life becomes more hostile in other ways. Nothing is given freely. Every innovation arrives with a bill. Still, life endures. It always does. Anaerobes hide deeper. Adaptable microbes invent new enzymes. Early communities reorganize. Oxygen-tolerant metabolisms gain ground. The biosphere, invisible and tireless, reshapes itself around a new reality. No speeches, no mourning ceremonies for lost lineages, just survival, expressed as chemistry. And above that chemistry, the sky slowly settles into a new mood. Ultraviolet light is no longer quite so murderous. Methane haze no longer dominates the view. Ozone quietly thickens far above. The air begins, molecule by molecule, to resemble the kind of atmosphere that future complexity will need. Not yet. Not fully. But enough to whisper that another kind of life may someday be possible. For now, though, the Earth is still mostly microbial, mostly silent, mostly red water and stone. The oxygen has only just begun its long campaign. It has rusted the seas. It has altered the sky. It has forced life into retreat and invention. And somewhere in that changing world, certain cells are about to attempt something astonishing. Not just survival in a new atmosphere, but internal complexity, partnership, and a redefinition of what a cell can be. That is the next door the Proterozoic opens. And as strange as the rusting seas already are, what comes after may be stranger still. Before we move on, stay with the oxygen a little longer, because it deserves the courtesy of being difficult. We like clean turning points in history. This happened, then that happened, and now here we are. The great oxygenation event refuses to behave that way. It is more like listening to someone learn an instrument through a wall. A note here, then silence. Then an awkward run of sound. Then a pause so long you wonder if they have stopped. Then another phrase, stronger this time. That is how oxygen entered the world. Unevenly, repeatedly, enough to change everything, but never in a tidy, straight line. In some shallow environments, oxygen may have accumulated during the day and almost vanished again at night. Photosynthetic microbes released it under sunlight. Darkness ended the supply. Respiration and chemical reactions consumed what remained. So even in places where oxygen was being made, its presence could have pulsed with light. Morning, a little rise. Evening, a fall. Over years, over millennia, over those vast Proterozoic spans, the pattern persisted. A daily rehearsal for a planetary transition. The sea itself must have felt different as chemistry shifted. Again, not to a hand or a face, since none existed to notice in the modern sense, but in terms of physical condition, different mineral precipitation, different cloudiness, different microbial layering. Surface films that once flourished under one balance of compounds now found themselves adjusting to another. Some mats thickened, some receded, some changed color. Modern microbial communities already show this kind of sensitivity. Slight changes in oxygen, salinity, pH, or light can redraw the internal architecture of a living mat within days. Now imagine that sensitivity played out over millions of years in the largest laboratory the Earth has ever offered. And perhaps the most unsettling detail is that no one was in charge. Not the cyanobacteria, not the oceans, not the atmosphere. There was no plan to make breathing possible. No intention to clear the sky. No purpose behind the rust. A few successful metabolisms spread because they worked for the organisms performing them. The world transformed as a side effect. That may be one of the oldest patterns in the history of life. The local act becoming the global consequence. As the old methane-rich atmosphere gave way inch by inch, climates grew more unstable. The cooling was not constant or uniform, but it had teeth. Ice began to matter in ways it had not before. Reflectivity rose. Weathering changed. Ocean circulation responded. The Earth, which had been chemically reworked by life, now started being climatically reworked by the after effects of that chemistry. It is one thing for microbes to stain the sea with rust. It is another thing entirely for them to help steer the planet toward ice. So while the oxygen spread, and while old lineages hid from it or learned to use it, the stage was being prepared for colder centuries, colder millennia, colder ages. The world had become more breathable in one sense and less forgiving in another. That is the Proterozoic way. Every opening comes with a narrowing. Every gift arrives wrapped in inconvenience. Still, what a gift it was. The first true oxygen in the air. The first real ozone overhead. The first skies edging toward blue. The first soils rusting under free atmosphere. The first chance, still unimaginably far from fulfillment, that life might someday step into shallower water, into open light, into forms larger than a film on stone. For now, though, the Earth remains between worlds, metallic but changing, quiet but restless, poisoned and improved at the same time. And beneath those cooling skies, certain ancient cells are on the verge of making a bargain that will echo all the way into our own bodies. A bargain built on partnership, hidden fire, and the strange possibility that one cell can survive best by keeping another one alive inside it. There is something almost tender about what happened next. After the long age of small, hard-working cells, after the seas had been rusted and the air had begun its awkward education in oxygen, life tried a stranger strategy than simple survival. It tried cooperation at close range. Not the loose neighborhood logic of microbial mats, not one layer passing waste to another, but something more intimate, more dangerous, more transformative. One cell took another inside itself and did not finish the job. If you were standing with me now, still somewhere along those old Proterozoic shores, the world around us would remain mostly quiet. No fish break the surface. No reeds bend in the wind. No wing shadows pass over stone. And yet inside the water, inside single drifting cells too small for the eye, an event of almost ridiculous importance is underway. Modern researchers have used AI to compare genomic remnants, metabolic pathways, protein architecture, and the chemistry of ancient environments, cross-checking their models with microbiology, evolutionary genetics, and the fossil record. What keeps coming back from those systems is the same unsettling suggestion. Complex life did not begin by building outward. It began by folding inward. The earliest cells had been practical creatures. Bacteria and archaea are still practical now. They do not waste energy on grandeur. They keep their DNA in the open. They run their chemistry in one interior space. They grow. They divide. They adapt with astonishing cleverness, but they remain stripped down in structure. A prokaryotic cell is like a traveler who owns only what can be carried on the back and still manages somehow to cross deserts, mountains, and poisoned seas. Efficient, tough, unsentimental. Then came the eukaryotic cell. Not at once, not in a dramatic unveiling, but as a gradual rearranging of what a cell could afford to be. There was now a nucleus, a membrane wrapped around genetic material like a room set aside for archives. There were internal compartments, structures devoted to separate jobs: transport, storage, processing. There was a cytoskeleton, a framework that gave shape and made directed movement possible. It was not just more complicated. It was a different philosophy of being alive. The leading explanation for this change still feels slightly scandalous in the best scientific way. An ancient host cell, probably archaeal in ancestry, formed an alliance with a bacterium capable of using oxygen efficiently. Maybe it engulfed the bacterium as prey. Maybe the bacterium entered by some softer route. Maybe the beginning was hostile and only later became useful. However it started, the relationship held. The internal guest kept doing what it did best, converting oxygen and nutrients into large amounts of usable energy. The host provided shelter, raw materials, and continuity. Over immense time, the guest gave up some of its independence. Genes moved into the host genome. Division synchronized. What had once been a separate organism became an organelle, the mitochondrion. It is one of my favorite moments in all of deep history, mostly because it is so unceremonious. No banner hung over the sea. No stone remembers the exact hour. Yet this quiet merger made your existence more likely. Mine, too. Every deep breath, every long thought, every heartbeat, every sleepy yawn you will make tonight depends on mitochondria still working inside your cells. Descendants of bacteria that moved indoors more than 1 billion years ago and never moved out again. You know that feeling when someone comes to stay for a weekend, and somehow 5 years later they are still there, using your mugs and paying half the rent. Evolution did that, only with vastly better consequences. The mitochondrion changed the energy budget of life. That matters more than it sounds at first. Energy is permission. With more of it, cells can afford internal structures. They can maintain larger genomes. They can make mistakes and repair them. They can move materials from one place to another. They can sustain shape, traffic, signaling. A cell with mitochondria is not merely stronger, it is richer in possibility. Complexity stopped being extravagance and became sustainable. The evidence for this old partnership survives in every modern eukaryotic cell. Mitochondria still carry their own DNA. They still divide in a way that feels bacterial. They still sit inside the cell like ancient tenants who have become family but never fully lost their accent. AI systems trained on comparative genomics have become very good at tracking such old inheritances, spotting which genes clearly originated in ancient bacterial lineages and which belonged to the host. The result is a picture of life not as a ladder climbed step by step, but as a series of mergers, bargains, and unlikely collaborations. This inward expansion of the cell opened doors everywhere. Some eukaryotes remained solitary. Others drifted into new environments. Some learned to engulf prey. That, too, was a novelty of enormous consequence. Once cells could swallow other cells intentionally, ecology gained a new flavor. Life was no longer only dissolving food from the environment. It was beginning to hunt on a microscopic scale. Predation entered the scene softly, but once it arrived, evolution gained fresh pressures. Escape began to matter. Detection began to matter. Shape began to matter. And then the partnerships deepened again. In some lineages, a eukaryotic host absorbed not an oxygen using bacterium this time, but a photosynthetic cyanobacterium. Another merger. Another quiet scandal. This guest became the chloroplast, the organelle that allows algae and later plants to turn sunlight into chemical energy. So the old blue-green architects of the oxygen revolution, those tiny cyanobacteria that had already changed the atmosphere, now entered a new phase of history by becoming part of other cells. They had transformed the world from outside. Now they began transforming life from within. It is difficult not to love the sheer audacity of that. The same lineage that poisoned ancient anaerobes and chilled the climate with its oxygen waste also became the green engine of future life. Deep time does enjoy a callback. The fossil record during this age is sparse in the way that all ancient microbial records are sparse. There are no triumphant statues of the first eukaryotes. What we get instead are microfossils, chemical signals, hints in preserved sediments, and the stubborn testimony of living cells that still bear ancient signatures. Some Proterozoic microfossils are larger than earlier bacterial forms, with shapes suggesting internal organization. Some show ornamentation or wall complexity. Certain molecular biomarkers hint at steroid-producing organisms, one clue often associated with eukaryotes. None of this gives us a single clean portrait, but together it becomes persuasive. Complex cells had arrived, and once they did, the pace of evolutionary imagination changed. Not quickly in a human sense. The Proterozoic never hurries, but steadily, quietly. New experiments began. Sexual reproduction appears sometime in this long middle world, and that is another lovely complication. For most of life before then, reproduction had been efficient and lonely. A cell divided. Its offspring were near copies. Mutation introduced change slowly. Reliable. Yes. Elegant, even. But limited. Sexual reproduction allowed cells to combine genetic material, shuffle chromosomes, and produce variation much faster. In a world of changing oxygen, shifting climates, and chemically layered seas, such flexibility was a profound advantage. And then there is multicellularity. Not yet the dramatic version with animals and forests, but the first gestures toward it begin here. Cells do not always separate cleanly after division. Some remain attached. Some communicate chemically. Some specialize a little. Cooperation thickens. Clusters become organized. Chains, sheets, and simple bodies start as a refusal to drift apart. The oceans of this age were still mostly microbial, still layered by chemistry, still carrying old iron memories and sulfur shadows. Yet they were changing in mood. Surface waters in some places held more oxygen now. Nutrient cycles were becoming more intricate. New ecological spaces opened for cells that could tolerate oxygen, exploit light, or consume one another. Eukaryotes did not instantly dominate, but they introduced a different texture to life. Some became predators, some photosynthesizers, some symbiotic hosts, some perhaps the earliest colonial forms. If you let your imagination settle on one ancient shallow sea at dusk, perhaps along the margin of an early supercontinent, you can begin to feel the difference. Microbial mats still spread across the bottom. Stromatolites still build their stone biographies. But now the water also holds larger cells drifting with internal scaffolds and nuclei. Cells carrying mitochondria that burn oxygen like small contained fires. Some engulf smaller prey. Some divide sexually. Some remain together after division a little longer than before. Nothing about the scene is theatrical. Yet the future has shifted. Life now contains within it the architecture for true complexity. There is a phrase people sometimes use for ancient worlds, saying they were primitive. I understand the habit, but it always feels unfair. Primitive compared with what? The Proterozoic was not failing to become the modern world quickly enough. It was inventing prerequisites. Oxygen, intracellular power, sex, multicellular cooperation. All of these are profound achievements. The age was not simple. It was foundational. And still the Earth refused peace. Even while cells learned intimacy and cooperation, the larger planet kept moving under them. Continents collided and split. Supercontinents gathered like slow great thoughts. Colombia, or Nuna, one of the earliest large continental assemblies of this era, drew ancient cratons together into a sprawling landmass. Later, Rodinia would form, another vast arrangement of continental pieces. Mountain belts rose where crust crashed together. Weathering stripped them back down. Nutrients washed into the sea. Carbon dioxide shifted through the air. Climate listened. Researchers now feed plate reconstructions, paleomagnetic data, geochemical records, and climate simulations into AI models that can test thousands of possible continental arrangements at once. What these systems show is that tectonics and biology were already dancing together. Uplift changed weathering. Weathering changed atmospheric chemistry. Atmospheric chemistry changed climate. Climate changed the opportunities available to life. No organism controlled the whole pattern, but every successful metabolism tugged at the web. Rodinia in particular matters, because once assembled, supercontinents tend to alter ocean circulation and climate profoundly. Large interiors become dry. Weathering patterns shift. Volcanism along rifts eventually releases gases and cracks new ocean basins open. These tectonic rearrangements do not merely change maps. They change what life can attempt. They change where nutrients gather, where ice forms, where shallow seas flourish, where oxygen accumulates. So while the internal world of the cell was becoming more elaborate, the external world was preparing one of its harshest tests. The atmosphere, partly transformed by cyanobacteria, had become more oxygenated. Methane had declined. Climate had become more fragile. Continents had assembled in ways that may have encouraged weathering and carbon drawdown. The stage was being prepared for cold on a nearly unthinkable scale. The first complex cells had arrived just in time to meet one of the most severe environmental ordeals the planet would ever invent, which feels, I admit, like a rather rude welcome. You spend 1 billion years inventing the mitochondrion and the nucleus and sex, and the Earth responds by trying to freeze itself solid. Typical. But that is the Proterozoic for you. Every triumph gets tested. Every innovation meets weather. Every partnership must prove it can endure not only abundance, but catastrophe. And the catastrophe approaching now is not local, not merely regional, but planetary. A freeze so vast that later generations would come to call the Earth a snowball. Not metaphorically, almost literally. So keep the fire low in your mind. Let the room cool a little as you listen, because the age of internal complexity is giving way to an age of ice. And the next thing the Proterozoic will ask of life is not invention, but endurance. The cold came slowly enough that no creature could have watched it arrive and understood the scale of what was happening. There were no creatures to watch in the modern sense anyway. Nothing with a face lifted toward the horizon in worry. Nothing keeping count of seasons. Nothing gathering food before the frost. But the planet itself was changing course. Oxygen had altered the atmosphere. Methane had declined. Weathering and tectonic rearrangements had pulled carbon from the air. And somewhere in the late Proterozoic, the Earth began to slip toward one of the strangest states it has ever known. Ice. Not a little at the poles. Not just mountain glaciers clinging to shaded heights, but cold so extensive that whole oceans may have sealed over and low-latitude regions carried glacial signatures. Modern researchers call these episodes Snowball Earth. And even now, the phrase sounds a little impolite, as if the planet had gone from ancient majesty to something a child might throw. Yet the evidence is stubborn. Glacial deposits appear in rocks that were laid down near the equator. Dropstones, carried by floating or melting ice and released into fine marine sediments, show up where no ordinary climate would place them. Ancient bedrock bears the scraped memory of moving ice. The world had entered a freezer big enough to reach the tropics. Modern climate models, many of them sharpened by AI, can now test thousands of atmospheric combinations, continental layouts, and ocean circulation patterns against the rock record. The same broad conclusion keeps returning. The late Proterozoic Earth did not merely cool. It may have crossed a threshold where ice began reflecting so much sunlight that the freeze fed itself. White surfaces reflected more light. Less absorbed heat meant more cooling. More cooling meant more ice. If you were standing with me on one of those continents before the worst of it, perhaps along a bare shoreline under a fading blue sky, you might not notice anything at first, except that the air felt sharper. The winds carried less warmth. Shallow waters chilled earlier and thawed later. Weathering patterns shifted. The ocean surface in quiet bays might take on a skin of ice that lingered longer than it should, over generations, over spans long enough to outlast mountains. Those signs multiplied. The sea edge pulled tighter. Ice spread. Light grew harder, less forgiving. Then imagine the ice reaching farther than sense can accept. Glaciers grinding over stone. Frozen oceans reflecting pale light back into a thin, cold sky. Continents wrapped in white silence. The sea, once metallic and microbially crowded, now dim under a lid of ice, perhaps hundreds of meters thick in places. It is one of the strangest images in Earth history, because our planet is so strongly associated with liquid water and motion. A frozen Earth feels almost mythic, and yet the rocks insist on it. What happened to life, then, is one of the most haunting questions in all of geology. Not because life disappeared. It did not. But because survival must have become a matter of hiding well and enduring quietly. Microbial communities in shallow waters would have been hit hard. Photosynthesis depends on light, and ice is a thief of light. Yet not all ice is equal. Cracks, thin patches, melt channels, and coastal refuges may have persisted. Beneath ice shelves today, microbial ecosystems survive in dimness that would seem absurdly meager to us. Hydrothermal vent systems in the deep sea would have gone on mostly indifferent to the frozen roof above, feeding chemotrophic communities that never needed sunlight in the first place. Some eukaryotes likely endured in these hidden places too. Under ice, around vents, in meltwater pockets, in brine channels where salts kept water from freezing solid, perhaps in open water polynyas maintained by wind, geothermal heat, or currents. Endoliths, microbes living inside rock, may have passed the long, cold, and quiet metabolic half-sleep. Dormant cells may have waited. The Proterozoic had taught life patience before. Now it demanded it. There is something almost monastic about that survival. No dramatic conquest of the ice. No triumphant adaptation montage. Just persistence. Reduced metabolism. Careful hiding. Chemistry performed at a whisper. And still the planet did not remain frozen forever. Volcanoes kept speaking from below. Even under a white world, the mantle moved, crust cracked, and carbon dioxide continued leaking into the atmosphere. Under normal conditions, weathering helps remove CO2. But with the continents locked under ice, that removal slows drastically. The gas accumulates, very slowly, relentlessly. The greenhouse effect begins to rebuild. The same atmosphere that had become vulnerable to cooling now becomes overloaded with trapped heat. Eventually, the balance tips the other way. Then comes thaw. No one should imagine it as a gentle spring morning. When a Snowball Earth begins to fail, it likely does so with drama. Darker patches absorb sunlight. Meltwater spreads. Ice retreats. Oceans reopen. Rain returns. Weathering surges over freshly exposed rock. Rivers flush minerals into the seas. Nutrients, long trapped in ice or newly freed from land, rush into marine systems. Carbonate layers, known as cap carbonates, are thought to record some of this aftermath. Sudden warm conditions laid down right after glacial deposits. The swing from frozen severity to hot greenhouse recovery may have been enormous. You know that feeling when a room has been closed up too long, and then someone finally throws open every window. Dust lifts. Air moves. Everything changes at once. The thawing Proterozoic must have felt like that on a planetary scale, though with much more acid rain and far fewer polite houseplants. This post-glacial world mattered deeply because it did not simply restore the old conditions. It created new ones. Oxygen levels climbed again. Nutrients from weathering fed productivity. Oceans, freshly mixed and chemically altered, became laboratories for further innovation. The long freeze may have squeezed life through an evolutionary bottleneck, not necessarily by inventing complexity directly, but by clearing space, reshaping habitats, and changing the chemical terms on which life operated. Around this time, the tectonic story continued its slow, enormous dance. Rodinia, that great supercontinent, had assembled earlier through collisions that built mountain belts on scales difficult to picture. But supercontinents are unstable things. Heat builds beneath them. Rifting begins. They crack apart. New ocean basins open. Pieces drift. AI-assisted plate reconstructions now compare paleomagnetic data, mineral ages, and ancient orogenic belts to test likely continental arrangements. The details remain debated, because deep time is never kind enough to leave a perfect map. But the broad pattern is clear. Rodinia broke apart during the Neo-Proterozoic, and that breakup changed everything from coastlines to currents to climate. Rifting would have produced long valleys, volcanic activity, and new shallow seas. Continental fragments shifted into new positions, altering albedo, rainfall, and the circulation of heat through the oceans. Some scientists think this tectonic rearrangement contributed directly to Snowball Earth by exposing fresh rock at tropical latitudes where weathering could draw down carbon dioxide more efficiently. Others emphasize complex feedbacks involving biology and ocean chemistry. It is debated. We cannot be sure of every lever that got pulled. But the levers were connected. Tectonics, atmosphere, ocean, biology. All of them moved together. And after the ice, the seas began hosting something new, or rather something newly visible. The late Proterozoic gives us the Ediacaran world, one of the most haunting biological intervals ever preserved. Imagine the seafloor of a quiet, shallow sea after the Great Freeze. Microbial mats still spread across the sediment, soft and cohesive, like living carpets. On top of them rest unfamiliar bodies, flat quilted forms, fronds, discs, lobed shapes, organisms that do not quite resemble anything alive now. They are too large to ignore, yet too strange to place comfortably. These Ediacaran organisms are preserved as impressions in ancient sediments, often in astonishing delicacy considering their soft bodies. They had no bones, no shells, no teeth, no proper faces. Some may have absorbed nutrients across their surfaces. Some may have fed more actively. Some seem anchored in place. Others may have moved slowly, leaving traces in sediment. The fossil record is maddening here, full of promise and silence at once. We see the forms, but the lifestyles remain partly hidden. Researchers now use AI to compare growth patterns and spatial distributions in Ediacaran fossil beds, helping paleontologists separate random damage from true body organization. Some forms grew in repeated branches. Others show bilateral order. Some may represent early animals. Others may belong to entirely extinct experiments in multicellularity. If you were standing with me by one of those late Proterozoic shores, after the thaw, and under a sky now clearer than in the ancient methane days, the sea would still not look lively in the modern sense. No fish schools, no reefs full of snapping jaws, but the bottom, where, visible through shallow water, would carry forms, real bodies, distinct outlines. Life had begun stepping into visibility. This matters because, for most of the Proterozoic, complexity was hidden. It existed in cells, in genomes, in metabolic pathways, in the internal architectures of eukaryotes. Now, complexity began to cast a shape into the world. Bodies, however strange, cease, however modest by later standards, development, however experimental. Life was no longer only a chemical film. It was becoming sculpture. At the same time, behavior began leaving marks. Burrows and trackways start appearing near the very end of the Proterozoic. Something with a front and back. Something with enough coordinated tissue to move through sediment intentionally was starting to engineer the seafloor. That changes ecosystems immediately. Burrowing introduces oxygen into sediment, redistributes nutrients, disrupts microbial mats, and creates new habitats. One small moving organism can alter an entire patch of ancient seafloor chemistry. The old microbial world, stable and layered, began to face disturbance from bodies that did not simply sit there. And that, perhaps more than any single fossil, signals the end of the old order. The Proterozoic does not end because it runs out of ideas. It ends because it has finally built enough infrastructure for a more visibly dramatic world to begin. Oxygen has risen, though not steadily. Complex cells exist. Mitochondria burn inside them. Sex shuffles genes. Multicellularity has taken hold in several lineages. Continents have assembled and broken. Glaciers have nearly sealed the planet and released it again. Nutrients pulse through recovering seas. Soft-bodied organisms occupy the seafloor. Burrowers begin to stir the mud. Every major prerequisite for the later explosion of animal life has been assembled by patience rather than spectacle. That is why the Proterozoic feels so haunting. It spent nearly 2 billion years doing the slow work that later ages would build on noisily. It invented the atmosphere we need, though very awkwardly. It taught cells to collaborate. It taught life to recover after global catastrophe. It made room in chemistry, in climate, in energy, in genetics. The end of the eon is not a hard stop. There is no cosmic gong, no invisible hand drawing a line between one page and the next. Instead, the world starts filling with more movement, more interaction, more visible complexity. By the time the Cambrian comes into view, many of the underlying conditions are already in place. The so-called explosion that follows is built on Proterozoic work, like fireworks launched from a platform hidden in the dark. And maybe that is the right way to leave this age. Not with some grand proclamation, but with a quieter gratitude for the long hidden labor of the world. The microbes that rusted the seas, the cyanobacteria that changed the sky, the first eukaryotic cells that turned roommates into organelles, the frozen earth that nearly closed the book and instead sharpened it, the soft, strange bodies resting on microbial mats under a recovering sun. You are carrying all of that now, whether you notice or not. Your cells still run on bacterial fire. Your breath still uses oxygen, first made dangerous by tiny ancient chemists. Your body still depends on the logic of cooperation, compartment, inheritance, and endurance worked out in those deep seas. Even your tolerance for bad weather is, in a distant biochemical sense, inherited from creatures that survived a nearly frozen planet by refusing to let go of life. The fire in the room is low now. The stone outside our imagined shelter is cold. The old seas are calmer for the moment. Somewhere far beyond them, the future waits with shells, eyes, and motion fast enough to leave a true shadow. But here, at the edge of the Proterozoic, the world is still mostly hush, still deep time, still carrying in its quiet the memory of rust, ice, and the first visible hint that life was ready to become something the rocks could no longer easily hide. And with that, the ancient silence begins to thin, just enough for the next age to start whispering through it. Above that old recovering world, the atmosphere kept learning how to behave. It had already survived its first great awkwardness, the long era of methane haze and oxygen scarcity. Then the chemical shock of the oxygen rise. Then the strange white glare of a nearly frozen Earth. But in the middle, and later Proterozoic, the air still had no intention of becoming modern in a neat or obedient way. It shifted, paused, climbed, and stumbled. It was not yet a finished sky. It was a draft, If you were standing with me on a bare craton shoreline in that age, perhaps on a slab of ancient rock that would one day sit under part of Africa or North America, the air would not feel familiar in the lungs. The world would not smell of grass or resin or warm soil after rain because there were no forests to offer such perfumes. There was only whetstone, mineral dust, shallow brine, volcanic breath in the far distance, and the thin, sharp scent of a planet still adjusting its chemistry. Modern researchers now use AI-assisted models to compare sulfur isotopes, iron oxidation signals, sediment layers, and atmospheric reconstructions, then cross-check them with climate physics and microbial metabolism. The result is not a single clean graph rising toward modern oxygen, but a nervous and complicated pulse. Oxygen increased, yes, but not with the confidence of a hero entering the last scene. It rose like someone finding a staircase in the dark, one hand on the wall, missing a step now and then, recovering, continuing. For long stretches of the Proterozoic, oxygen levels were still low by modern standards. Enough to alter minerals and weathering patterns, enough to build an ozone layer that slowly softened the sun's ultraviolet cruelty, enough to open ecological doors for certain cells, but still not enough to make the world feel lush, active, or crowded. Many geochemists call part of this interval the boring billion, which I have always found a little unfair. It is a wonderfully human insult. If 1 billion years does not produce enough dinosaurs for us, we call it boring. The rocks, I think, would object, because underneath that supposed boredom, the atmosphere and the biosphere were learning each other in extraordinary detail. Carbon dioxide moved through volcanic emissions, weathering reactions, burial in sediments, and returned through tectonic recycling. Methane, once a dominant warming blanket, had been reduced by oxygen chemistry. Sulfur cycled through oceans, air, and microbial metabolisms. Nitrogen remained an important background presence, quiet but essential, a kind of patient clerk keeping the paperwork of life in order while oxygen and carbon took turns causing scenes. Ozone deserves more affection than it usually gets in casual storytelling. It is not glamorous. It does not build skeletons or write itself dramatically into fossils. Yet it was one of the great protective gestures in planetary history. Once enough oxygen accumulated in the upper atmosphere, ultraviolet light split some oxygen molecules apart and allowed ozone to form. A shield developed. Not perfect, not immediate, but increasingly important. For the first time in Earth's history, the surface and shallow waters became less murderous to delicate organic molecules. The sun had not softened. The air had learned to intercept the blow. That change matters more than it seems. Before an ozone layer, life stayed underwater or inside rock or sediment because the surface was an irradiated hazard. With ozone, windows opened. Shallow habitats became safer. Later, much later, land itself would become an option. The Proterozoic was not only inventing oxygen, it was inventing permission. Climate listened to all of this with unnerving sensitivity. A little less methane and the world cooled. A little more volcanic carbon and the world warmed. Exposed rock on rifting continents drew down carbon dioxide through weathering. Buried organic material shifted atmospheric balances. Ocean circulation, altered by changing continental arrangements, redistributed heat and nutrients differently. Earth, during this eon, was like a great chemical instrument that kept discovering new notes and accidentally shaking the room with them. And through all of that atmospheric improvisation, life remained mostly microscopic, though no longer simple in the way it had once been. Eukaryotic cells had already emerged, those internally organized descendants of ancient mergers, and with them came the possibility of a new kind of evolutionary experiment. Sex. It still amazes me that sexual reproduction became so successful, because, on paper, it looks like a deeply inconvenient idea. A cell that can simply divide and make a near copy of itself seems to have the more efficient arrangement. No need to find a partner. No need to split a genome in half and hope the mathematics works out. No need to risk bad combinations or the whole fragile ceremony of fusion. And yet somewhere in the Proterozoic, eukaryotic cells developed a way to exchange and recombine genetic material so effectively that it changed the future of life. AI tools trained on comparative genomics have helped biologists estimate just how ancient the core machinery of meiosis and recombination may be, cross-referenced with molecular clocks and the fossil record. The picture suggests that sexual processes appeared deep in this eon, long before animals, long before flowers, long before anything anyone would romantically write a poem about. The first sex on Earth was not candlelight and longing. It was chromosomes being carefully pulled apart in single cells drifting through an ancient ocean. Still beautiful, in its way. Before sex, inheritance had been largely about copying plus mutation, reliable, efficient, and slow in what it could explore. With sex, genomes could be reshuffled. Traits could be recombined. Harmful mutations could be masked or purged more effectively. Populations could generate diversity faster, which in unstable worlds is a magnificent advantage. Oxygen fluctuations, climate swings, freezes, shifts in ocean chemistry, all of these made flexibility valuable. Sex did not guarantee survival, but it made adaptation far more agile. You know that feeling when a room has been rearranged and suddenly you can use it in new ways, simply because the furniture is no longer where it always was. That is roughly what sex did to the genome. Same components, new combinations, new possibilities. And suddenly evolution had more ways to surprise itself. This was also a social turning point, though calling it social is perhaps a little generous for single cells. Still, interaction became more structured. Recognition mattered. Timing mattered. Compatibility mattered. Cells had to communicate chemically, respond to one another, fuse or exchange material with enough precision to avoid disaster most of the time. Cooperation was no longer only about living next to another cell. It was about sharing inheritance. That habit of collaboration did not remain confined to reproduction. In lineage after lineage, cells that had learned to coordinate began trying something else, remaining together. At first, the step toward multicellularity may have been almost embarrassingly small. A cell divided, and its offspring did not fully separate. 2 became 4. 4 became 8, all still clinging by membranes or secreted substances. In some cases, this was temporary. In others, it became advantageous. A cluster could resist being engulfed. A group could move or sink differently. Some cells on the outside might absorb nutrients or light more effectively, while others inside gained protection the moment any of those roles became even slightly specialized. Natural selection had something new to work with. Multicellularity evolved several times, which tells us it was not a miracle so much as an opportunity waiting for enough energy and enough genetic control. Cyanobacteria had already formed filaments and colonies. Certain eukaryotes began building more persistent bodies. Small at first, often little more than sheets, spheres, or branching forms. Cells signaled to each other. Some stopped reproducing and started supporting. Others handled movement or attachment. A body is, in the end, a treaty. Not always fair. Usually effective. Energy made the treaty possible. Mitochondria gave eukaryotic cells a richer internal budget. With more ATP available, cells could afford to maintain structure, signaling systems, cytoskeletal scaffolds, and developmental regulation. Oxygen in the environment, though still fluctuating, increasingly supported these more expensive arrangements. The old microbial world had been powerful, but it was metabolically austere. The Proterozoic was now experimenting with luxury. The rocks preserve hints of these experiments. Larger acritarchs, ornamented microfossils, suggest complex single cells or simple multicellular organisms. Some fossils appear as filaments or clustered colonies with patterns difficult to explain as mere accidents of preservation. AI pattern recognition has even been used to compare growth symmetry and wall textures in these microfossils, helping researchers sort real biological structure from mineral trickery. What emerges is not certainty in every case, but a direction. Life was getting organized, and organization changes everything. Once cells become a functioning collective, selection can act not only on the cell, but on the group. Shape matters. Size matters. Division of labor matters. The body itself becomes a unit of evolution. Even the simplest multicellular forms carried a promise within them, that living things might become larger, stranger, and more spatially ambitious than anything bacteria and archaea had ever attempted. The atmosphere and biology were now in a feedback relationship so intimate, it is difficult to say where one ended and the other began. Oxygen enabled new metabolisms and larger bodies. Those bodies, in turn, changed the carbon cycle, nutrient use, and ecosystem structure. Sex increased variability. Variability allowed experimentation. Multicellularity turned cooperation into architecture. Architecture would soon become ecology. Yet the Proterozoic still refused spectacle. Even its great innovations arrived quietly. There were no forests waving in the wind, no fish flashing through reefs, no beetles climbing stems. The seafloor in many places was still carpeted in microbial mats, and the most consequential events were still happening at scales too small for the naked eye. But if you could kneel by one of those late Proterozoic shores and dip your hand into the water, the future would already be there. In the oxygen dissolved near the surface, in the drifting eukaryotic cells carrying mitochondria, in the gametes or fusion events no eye could see, in the little colonies refusing to separate, It is such a wonderfully Proterozoic move. Really, to reinvent the structure of life itself and do it all with almost no audience. Still, the audience was coming. As oxygen levels improved and the post-glacial world settled into new chemical possibilities, multicellular experiments expanded. Some lineages stayed microscopic, others edged upward in size. Some remained colonial, loosely arranged. Others began developing more coherent body plans. By the late Neoproterozoic, the stage would hold forms large enough to leave visible impressions in sediment. Strange fronds, quilted discs, flat bodies resting on microbial mats, like ideas trying out shape for the first time. But before those ghostly Ediacaran communities spread across the seafloor, the world had to finish learning a few more lessons in chemistry, inheritance, and patience. That is the true mood of this age, I think. Patience with consequences. The atmosphere taking 1 billion years to clear its throat. Cells taking an age to trust each other with genomes. Small clusters of life, rehearsing the possibility of bodies, while the continents ground against one another in the background like slow, unseen machinery. If you were standing here with me now, under that ancient sky, the scene would still feel almost empty by later standards. Bare rock, shallow water, wind with no leaves to trouble. The silence would be enormous, but it would no longer be the silence of a world that has not begun. It would be the silence of a world concentrating and out in the water, in forms so small they would seem like nothing at all. Life would be making choices that every animal and every plant would inherit. How to share energy, how to mix genes, how to stay together, how to become more than one. The old microbial empire was not ending. It was being joined by a new kind of ambition, one that would eventually cover the seafloor with bodies, and then the land with forests, and later the air with wings. The Proterozoic still held all of that in reserve, but reserve is not absence. It is preparation. So let the air in your imagination settle now, thin and cool and newly protective. Let the water hold its quiet chemistry. Let those first complicated cells divide, merge, and remain together just a little longer than before. Because the next step in this long, deep story is the moment when life stops being almost entirely invisible and begins, very gently, to take shape in public. By the time the later Proterozoic drifted toward its close, the world had become stranger in a more visible way. For nearly 2 billion years, the great work of life had been mostly hidden, conducted in cells, films, mats, and chemical exchanges too small for any future eye to admire. Then the seafloor began to hold forms. Not fish, not crabs, not anything you would point to in a tide pool today and recognize with relief. These were the quiet citizens of the Ediacaran world, soft-bodied, often flat, sometimes frond-like, sometimes quilted, sometimes so perplexing that even now paleontologists look at them with the expression of people trying to read a language that only almost wants to be understood. If you were standing with me beside a shallow Ediacaran sea after the last great ice had withdrawn, the surface might seem calm enough to disappoint a modern traveler. No leaping fins, no shells clattering in the wash, no birds, because there were no birds. No reeds because there were no plants on land. No beach grass, making the whole thing look properly alive. And yet beneath the water, on and within the sediment, the world was busier than it had ever been. Microbial mats still spread across the seafloor, those old layered veterans of deep time, cohesive and slightly rubbery under the water, trapping sediment, controlling microchemistry, and preserving surface impressions with a devotion any museum curator would envy. Resting on or within these mats were bodies, real bodies, organized multicellular lives with outlines large enough to be seen, in rare, good conditions, to be fossilized. Modern research teams now use AI image analysis to compare entire fossil surfaces from Ediacaran sites around the world, from Namibia to Australia to Newfoundland, mapping repeated growth patterns, branching rules, symmetry, spacing, and overlap. Cross-checked with sedimentology and taphonomy, the results show something both thrilling and maddening. These organisms were not random soft blobs. They were structured, patterned, in many cases mathematically disciplined in their growth, yet many do not fit neatly into later animal categories. Some forms looked like fronds pinned to the seafloor, rising gently into the water column from holdfast discs. Others looked like flattened leaves with repeated side branches arranged in exquisite symmetry. Some resembled stitched quilts. Some sat as discs or low ovals. Some may have moved. Trace fossils from the latest part of this era hint that certain organisms glided or crept across sediment, leaving faint marks that suggest intention without hurry. I have always loved how odd these beings are. They do not arrive in the fossil record with the confidence of familiar success. They arrive like prototypes, like drafts of embodiment, as if life had spent ages learning how to build a body and then, once the chance finally came, tried several versions at once just to see what might hold. One of the first things to understand about the Ediacaran world is that it was not crowded in the modern sense. Many bedding planes show organisms spaced apart, each occupying its own patch of seafloor. This was not yet an age of frantic competition, biting jaws, or constant pursuit. It was quieter. Bodies were larger, yes, but ecosystems still had a long contemplative quality. The seafloor was not a battlefield. It was more like a gallery of cautious experiments. Some researchers argue that many Ediacaran forms were early animals, perhaps related in distant ways to cnidarians, bilaterians, or lineages now long gone. Others think some may represent entire branches of multicellular life that left no descendants. It is debated. We cannot be sure. That uncertainty is not a weakness of the story. It is part of its mood. The Proterozoic has always been a master of half-light. AI-based growth models have been especially useful here because certain Ediacaran organisms seem to have developed through repeated modular branching, patterns that are easier to detect statistically than by eye alone. Some grew by adding units at precise intervals. Others expanded with near fractal order. These are not sloppy accidents pressed into mud. They are bodies following instructions. And instruction is the key word. Development had become a meaningful force. Cells were no longer merely stuck together. They were coordinating where to grow, how much to grow, and in what relation to one another. A body plan, however alien, is a sentence written in time by genes and cellular signals. The Ediacarans were writing some of the first long sentences. There is also something deeply restful about them. Most had no obvious mouths, no hard teeth, no evident eyes. Some may have absorbed nutrients directly from seawater. Some may have grazed on microbial films. Some may have filtered. Their lives were likely slow, paced by oxygen, still modest by modern standards, and by ecosystems where movement was possible, but not yet dominant. Imagine broad, quiet seabeds under dim, greenish light, microbial mats stretched like old woven cloth, and soft forms anchored or resting there, letting currents pass over them for years. Then, slowly, movement became more important. Burrows appear in the later record. Sediments begin to show disturbance from organisms passing through them. That is a profound ecological shift. A burrow is not just a tunnel. It is a declaration that life has started editing the seafloor. Oxygen enters sediment more deeply. Nutrients are mixed. Microbial mats are interrupted. The old, stable, layered world begins to break. If you want a symbol of the end of the Proterozoic old order, it may not be some spectacular creature. It may be the first animal, or animal-like organism, that decided to push through the mud, and in doing so, ruin a perfectly good microbial carpet. The close of the Proterozoic is full of these gentle revolutions. Sexual reproduction has spread among eukaryotes. Multicellularity is no longer a novelty. Development has become capable of producing visible form. Oxygen is high enough in at least some settings to support larger bodies and more active metabolisms. Continents have reorganized. Oceans after the Snowball episodes are chemically changed. Nutrients surge through recovering systems. The world is not modern, but it is becoming permissive in a new way. And from this permissiveness comes transition. The end of the Ediacaran and the beginning of the Cambrian are often spoken of as if someone suddenly turned on the lights and released every strange animal at once. Reality is more patient than that. The famous Cambrian radiation was built on Proterozoic groundwork, on all the slow inventions that came before. Oxygen, mitochondria, sex, multicellularity, body planning, ecological disturbance. None of these appear from nowhere. They are Proterozoic gifts handed forward. That is why I find this eon so moving. It never gets the dramatic praise given to dinosaurs or even to the Cambrian itself. But it is the age that built the platform. It oxygenated the atmosphere. It reorganized the oceans. It taught cells to cooperate, to merge, to specialize, to reproduce in richer ways. It endured global freezes and still carried life through them. It brought forth the first visible experiments in larger bodies. It did all of this so slowly that the mind struggles to hold the timescale without feeling a little dizzy. Honestly, that dizziness is part of the lesson. Human history likes a quick plot. Beginning, middle, end. Vilain, if possible. Some useful jewelry. The Proterozoic offers none of that. It offers duration. It offers patience so extreme that it becomes a kind of moral instruction. Not everything important arrives loudly. Not every transformation looks impressive while it is happening. Sometimes the deepest revolutions are microbial. Sometimes the whole future of life depends on a quiet cell deciding not to digest its bacterial guest. Sometimes the atmosphere changes because billions of tiny organisms keep exhaling a dangerous gas for long enough that the planet can no longer ignore it. And then there is the most intimate truth of all. The Proterozoic is not merely behind you. It is in you. Every eukaryotic cell in your body still runs on ancient bacterial machinery. Your mitochondria are descendants of those once free organisms that moved indoors in deep time. Your genome is managed inside a nucleus, one of the great structural inventions of early complex cells. Your existence depends on oxygen, that old Proterozoic pollutant turned metabolic blessing. Sexual reproduction shaped the lineage that produced every ancestor you have. Multicellularity is not abstract history. It is the reason you have tissues, skin, muscle, memory, even your vulnerability, your aging, your molecular repairs and small mistakes. All of it traces back to systems first assembled in that eon. You are, in a very literal and biological sense, a Proterozoic echo. If you look at your hand in the quiet after hearing all this, really look at it, you are seeing the outcome of ancient negotiations between cells, between host and symbiont, between metabolism and atmosphere, between chance and endurance. Nothing in the Proterozoic was trying to make you. Evolution does not think ahead that way. But the conditions that allow you to exist were built there, layer by layer, one immense silence after another. The continents, too, still carry the memory. Ancient cratons formed and stabilized in this eon still sit beneath modern landmasses like old bones under fresh skin. Iron formations laid down in rusty seas are mined today. Glacial deposits from snowball worlds remain scratched into rock. Sediments preserve the first visible bodies and the first traces of movement through mud. The eon did not vanish. It hardened into the foundations of the world and into the chemistry of the atmosphere that now fills your lungs. And so when the Proterozoic comes to its end, it does not feel like a closing door so much as a curtain thinning. Through it you can already sense what is coming next. More oxygen, more motion, more ecological conflict, shells, predation, eyes, bodies that can chase and flee and dig and bite. The old hush will not survive much longer. The Cambrian world is waiting just beyond the threshold with all its noisy ambition. But before we leave this age entirely, I want to linger for one more quiet moment at one of those late Proterozoic shores. The rock underfoot is still bare. The air is clearer than it used to be, though not quite ours. The tide breathes over microbial mats. Somewhere offshore, a strange fronded body leans in the current. Beneath the sediment, a small moving thing leaves a delicate line through mud. Above, the sky is blue enough now that if there had been eyes to appreciate it, someone might have thought it beautiful. No one did. Not yet. But the beauty was there anyway. That may be the deepest charm of this eon. It built so much for an audience that did not yet exist. It prepared oxygen before lungs. It prepared ozone before landwalkers. It prepared sex before courtship, bodies before beasts, seabeds before burrowers, and ecosystems before food webs had any real teeth in them. the Proterozoic worked in advance, patiently, invisibly, generously. And because of that, we inherited a world that could eventually become visible, audible, and restless. A world with weather over forests, rivers through soil, animals with shadows, minds capable of wondering where they came from. When you trace that wondering back far enough, you do not stop at the age of dinosaurs or even at the first animals. You arrive here, in the long, mostly silent Middle Age of Earth, where life learned how to become complicated without ever losing its small original genius. So let the mind settle now. Let the ancient ice recede one last time. Let the microbial mats glow faintly in memory. Let the first complex cells drift. Let the first strange bodies rest on the seafloor, while the continents move with ancient slowness above the mantle. And let yourself remember, in the gentlest way, that the quietest ages are often the ones that matter most. The Proterozoic did not end because it failed. It ended because it had finally done enough. It had prepared the atmosphere, the cell, the body, the seafloor, and the possibility of everything noisy and visible that would follow. It had written the first long chapters in a language of chemistry and stone. The next eon would turn those chapters into drama. But this one, this old, blue, and rusty, and icy, and patient world, remains beneath it all. A hidden inheritance. A deep old murmur under every breath you take. And if the room feels a little quieter now, that seems only fair. We have been walking through nearly 2 billion years of whispered preparation. It should leave a hush behind. Hold on to that hush for a moment longer, because the next age will not be nearly so polite. By the close of that immense old age, the world had become both more familiar and more uncanny. The air carried more oxygen than it once had. The seas, though still strange in places, could now host larger and more organized lives. The continents were no longer only low, anonymous slabs of stone. They had histories, saturs, collisions, wounds. The ice had come and gone more than once, and on the seafloor, in the hush beneath the water, the first visible experiments in complex life had settled themselves into the mud like thoughts becoming shape. What we call the Ediacaran world was not crowded the way later oceans would be crowded. It was not full of snapping mouths, darting fins, or shelled armies. It was softer than that, quieter, almost ceremonial in its pacing. If you could drift down through that water with me, the light above would already feel changed from the older world. Clearer in some places, more blue, more open. The ozone shield above had done its long, patient work. The surface was not yet home to plants or wandering animals, but the sea had become more welcoming to bodies that needed a little more energy, a little more room, a little more stability. And there, spread across the seafloor, you would begin to see them, broad quilted forms pressed gently into the sediment, frond-like bodies rising a little from circular anchors, disc-shaped impressions that seem at first glance like something simple, until you look again and realize they are organized, deliberate, patterned. Some scientists compare them using AI systems that measure branching angles, modular, repetition, body symmetry, and surface proportion across fossil slabs from Australia, Newfoundland, Namibia, and Russia. Those models do not solve the mystery, but they make one thing very clear. These were not casual accidents of preservation. These were bodies with rules. Some of them may have been among the earliest animals. Some may have belonged to lineages that vanished completely, leaving no descendants and no easy explanation. It is debated. We cannot be sure. And that uncertainty gives the whole Ediacaran world a haunted kind of dignity. It was real. Certainly real. Yet in many ways, it still stands just beyond our confident understanding. Like a half-remembered room in a house that no longer exists. Many of these organisms did not seem built for rushing. They had no obvious jaws, no hard skeletons, no signs of muscular power, the way later creatures would show it. They may have absorbed nutrients directly from the water, or lived in close relation with microbial films, or fed in ways that no longer have close modern parallels. They rested. They extended. They branched. They occupied space. And that alone was already a revolution. For most of Earth history before this, life had been chemically rich, but physically restrained. It changed oceans, altered the atmosphere, rusted iron, cooled climates, survived under ice, and rewired the future, all while remaining almost entirely microscopic. Now life had begun to show itself in outlines. It had become architectural. Honestly, I find that more moving than the arrival of the famous later beasts. There is something tender about these first visible bodies. They do not stride onto the stage with confidence. They seem to be testing the stage boards with bare feet, wondering whether shape itself will hold. Modern researchers feed thousands of fossil images into neural networks to separate real biological pattern from wrinkles, cracks, or distortions in the rock. Those systems compare margins, growth modules, radial and bilateral balance, and sediment texture. Then archaeologists, paleontologists, then geochemists check the flagged patterns by hand. What emerges is a world that was beginning to structure itself in public. Development had become visible. Cells were no longer only cooperating inside hidden colonies. They were making bodies large enough to leave an impression that could survive 500 million years. The seafloor itself changed in response. Some of the later traces from this time suggest movement. Not elegant swimming or dramatic pursuit. Nothing so theatrical. More like gentle repositioning. A shift across the mat. A careful glide or crawl over soft sediment. But even that tiny gesture mattered. Because once an organism moves through sediment, the sediment is altered. Oxygen penetrates differently. Microbial communities are disrupted. Layers that had remained quietly stable for ages are suddenly mixed. This is one of my favorite details in all of deep history, because it feels both monumental and slightly rude. For billions of years, microbial mats had organized the shallow seafloor with patient authority. And then along comes some small, soft thing with a body plan and a destination, and begins to mess up the carpet. That small disturbance was the beginning of a much larger change. Ecosystems were becoming interactive in a new way. Not merely chemistry drifting through layers, but bodies occupying positions, moving through gradients, affecting each other by presence and contact. The old microbial order was not ending. Not yet. but it had gained neighbors that would not always be polite. At the same time, the chemistry of the planet was still shifting beneath this rise in visible life. Oxygen levels were higher than before, though still lower than modern levels. Nutrients surged in some post-glacial oceans. Continents rearranged. Weathering drew elements into the sea. The atmosphere and oceans still behaved like a system learning itself, adjusting, responding, overshooting, recovering. There was no stable finish line, only a widening of possibilities. And then, toward the final stretch of the Proterozoic, the signs multiply. More trace fossils, more evidence of purposeful motion, more variety in body forms, more suggestion of front and back, top and bottom, maybe even primitive coordination that would one day become the nervous dramas of later animals. Still no grand spectacle, but the silence had changed. It now contained anticipation. You can almost feel the planet leaning toward a threshold. The threshold is what matters here. We often speak of the Cambrian explosion as if life had been sitting patiently in the wings for billions of years and then suddenly burst through the doors in full costume. But nothing in the Cambrian makes sense without the Proterozoic preparation. The oxygen had to rise. The ozone had to form. Eukaryotic cells had to emerge from those ancient mergers. Sexual reproduction had to spread. Multicellularity had to become stable. Development had to learn how to produce bodies. Ecology had to move from passive chemistry toward interaction. The Ediacaran world did not fail because it was replaced. It succeeded because it made replacement possible. Still, the end of that world carries a quiet sadness. Many Ediacaran forms disappear. Their quilted bodies, their fronded arrangements, their soft, strange symmetry fade from the record. Whether they were outcompeted, transformed, or simply overtaken by ecosystems that no longer favored their style of living, we do not fully know. The coming age would reward motion, burrowing, active feeding, armor, competition. It would reward disruption. The old stillness could not dominate forever. I imagine those final Ediacaran seafloors as beautiful in a way we no longer have. Broad fields of microbial mats under cool water. Sparse, soft bodies arranged with almost meditative spacing. Currents passing over them. Sediment settling lightly between them. All while somewhere nearby new organisms begin to tunnel, graze, stare, and complicate. The old world was not shattered in an instant. It was gradually out-argued, and then comes the edge itself, the place where the Proterozoic gives way to the Phanerozoic, the great age of visible life. It is not a clean line in reality, even if textbooks enjoy drawing one. Boundaries in geology are often a little like coastlines in fog, useful from a map, less precise up close. But there is a real transition. Burrows become more common. Hard parts begin appearing. Body plans diversify in ways that no longer feel tentative. Predation intensifies. The seafloor is churned more aggressively. Evolution changes tempo. The Proterozoic does not end because it is exhausted. It ends because the work it was doing has finally accumulated enough force to spill into a new style of living. That is, I think, the gentlest way to understand this age. Not as a waiting room, not as a dull prologue, but as the long engineering phase of life. The age that built oxygen from microbial waste. The age that endured snowball worlds and still recovered. The age that invented the eukaryotic cell through partnership. The age that developed sex, multicellularity, visible bodies, and the first ecological disturbances complex enough to feel like the beginning of animal history. Without this eon, there is no later drama. No trilobites crossing seabeds. No forests darkening continents. No reptiles, mammals, birds, insects, or hands like yours resting somewhere in the dark while listening to a story. This old world of microbes, rust, ice, and patient chemistry made all of that possible. And it did so mostly without spectacle. That remains my favorite part. It is such a quiet triumph. A billion here, a few 100 million there, cells merging, gases shifting, oceans freezing, thawing, continents colliding, all while life continues to improvise with microscopic stubbornness. If history were fair, the Proterozoic would get a little more applause. But perhaps it does not need applause. Perhaps being foundational is enough. If you were standing with me now at one of those very late Proterozoic shores, just before the world tipped fully into the Cambrian, the air would feel cooler than modern tropical air, cleaner in some ways, harsher in others. The rock would still be bare. No roots would split it. No moss would soften it. The sea would breathe in and out against stone, with nothing leafy on shore to answer it. And yet beneath the water, if you could see clearly enough, the future would be everywhere. In a tunnel pressed through soft sediment. In a body that now has front and back. In a clustered set of cells that no longer behave as equals but as parts. In the first signals of a biosphere about to become louder. The curtain was not falling. It was lifting, and when the next age arrived, it would arrive carrying the full inheritance of this one. Oxygen in the air, complexity in the cell, memory in the genome, geometry in the body, and a planet no longer merely habitable for life, but increasingly shaped by life in return. That shaping had only just begun. The Cambrian would make it obvious. But the Proterozoic had already done the hard part. It had built the stage, tuned the light, arranged the chemistry, and taught life how to stand where it could finally be seen. So let the strange fronds rest a little longer in your mind. Let the quilted bodies keep their patient places on the seafloor. Let the first burrower make its mild scandal through the mat. Let the blue of the sky, still new in deep time, settle above a world that has nearly finished becoming ready. Because in the next movement of the story, readiness will turn into abundance, and quiet possibility will turn into visible life. There is another way to see this threshold, and I think it is worth taking slowly. For all the attention later ages give to sharp teeth, hard shells, and visible struggle, the most radical thing at the end of the Proterozoic may have been simply that life had become capable of occupying space with intention. A body on a seafloor changes flow. It casts a shadow. It interrupts sediment. It creates edges where chemistry behaves differently. Even before predation became obvious, presence itself had become ecological force. That means the planet was no longer being shaped only by invisible metabolisms and broad atmospheric consequences. It was beginning to be shaped by arrangement, by where one organism rested relative to another, by whether a frond lifted into moving water or lay flat, by whether a soft body stayed still on the mat or crossed it. Ecology was learning geometry. And geometry matters. AI-assisted reconstructions of fossil beds show repeated spacing relationships that suggest certain Ediacaran communities were not randomly distributed, whether by larval settlement, current patterns, nutrient competition, or simple growth constraints. They formed living fields with order. The seafloor had become a map. Life was not only changing the planet chemically, it was beginning to compose it spatially. That spatial awareness would soon become one of the great themes of the living world. Territories, reefs, forests, burrows, nests, cities, all of them descend in some far patient way from this moment when bodies first began to matter, not just for what they were made of, but for where they were. When we speak about the Proterozoic ending, it is tempting to imagine some dramatic handoff, a trumpet call from geology, a neat final page turned from one chapter to another. But the truth, as usual, is more patient and more beautiful. The Proterozoic did not end in panic. It ended by giving almost everything away. By then, the atmosphere had been transformed from a place nearly empty of oxygen into one that could support far richer metabolisms. The oceans had passed through iron-rich darkness, sulfurous layering, global freezing, and renewed circulation. Continents had assembled and broken apart. Ancient cratons had survived the violence and remained as stubborn foundations. Eukaryotic cells had emerged from profound symbiosis. Sex had begun reshuffling inheritance. Multicellularity had become more than an experiment. The first visible bodies had lain themselves upon the seafloor. Sediment had been stirred by purpose, however slight. The old invisible world had opened a door and something more dynamic was already stepping through. So no, the Proterozoic did not go out with fireworks. It went out like a teacher leaving a room while the students, finally capable of making their own noise, began talking all at once. And perhaps that is why I find it so hard to think of this eon as remote in the way people often do. It is ancient beyond comfortable comprehension. Yes, nearly 2 billion years of change. Time so large, it makes empires and languages feel like sparks from a fire that vanish before they land. But ancient is not the same as absent. The Proterozoic still lives inside the present with astonishing intimacy. You are breathing an atmosphere that this eon helped build. That is not a metaphor. Every breath you take relies on oxygen becoming common enough in the ancient world to support high-energy metabolisms. Before the oxygenation of the atmosphere, before ozone formed overhead, before the chemistry of the oceans shifted and the planet learned to tolerate this reactive gas, the kind of complex body you inhabit would have been impossible. You would not merely be absent. The conditions required for anything like you would not have existed. And deeper still, your cells remember. Every eukaryotic cell in your body carries the architecture of those old innovations. A nucleus protecting and organizing DNA. Mitochondria descended from once free-living bacteria, still with their own tiny genomes, still whispering their bacterial ancestry through double membranes and ancient biochemical habits. Your metabolism is not modern in origin. It is a layered inheritance from mergers that took place in waters no animal ever saw. When modern biologists use machine learning to compare mitochondrial genes across living organisms, cross-referencing them with bacterial genomes and evolutionary trees, what they recover is one of the clearest memories life has kept. We are composites. Complex cells did not arise by pure isolation or heroic self-invention. They arose by partnership, by one ancient life form taking another inside and, for once in the history of eating, deciding to keep it. Honestly, I think there is something comforting in that. Life did not become complex by becoming pure. It became complex by becoming entangled. You carry that entanglement now, in your muscles when they work, in your brain as it burns energy to imagine this old world, in your heart as it keeps steady time while you listen. Every animal body is a kind of ancient agreement signed between lineages that once met in the dark and stayed together. Sex, too, that strange, risky invention of deep time, remains with us, not just as reproduction, but as inheritance itself, as the shuffled and recombined line through which every ancestor reached you. The Proterozoic world discovered that variation could be built more quickly by mixing genomes than by waiting on mutation alone. That decision, repeated across ages, gave life flexibility, resilience, and range. Every family resemblance, every inherited trait, every odd little detail passed down through generations has roots in that ancient cellular gamble. Then there is multicellularity, the old choice not to separate, to remain together after division, to specialize, to surrender some independence so the whole can become more capable than any one part. You are made of cells that gave up the right to go their own way. Skin cells do not decide to become neurons. Liver cells do not wander off to play at being bone. The discipline of the body, the cooperation of tissues, the quiet loyalty of specialization, all of that belongs to a world that began learning these rules in the Proterozoic, and the planet around you keeps its marks as well. The iron formations, mined from ancient rocks, are the rusted memory of oxygen first reacting with old seas. The great stable cores of continents beneath North America, Africa, Australia, and elsewhere are survivors from that age of tectonic organization. Glacial deposits, preserved in improbable latitudes, are the signature of snowball episodes when Earth came terrifyingly close to locking itself under ice. The fossils of strange Ediacaran bodies remain pressed into stone like notes from a language that was almost spoken longer. Even silence itself feels different after spending time with this eon. Human life is noisy, almost by default. Not just machines and cities, but speech, music, footsteps, doors, dishes, roads, messages. We are surrounded by constant interruption. The Proterozoic offers another scale of experience. Vast intervals in which the most important events are chemical, cellular, glacial, tectonic. It reminds us that significance does not require speed, and that drama does not always arrive with sound. You know that feeling when a room has been changed in some tiny but essential way, and you cannot immediately say what is different. only that the whole mood has shifted. That was the Proterozoic for Earth. It changed the mood of the planet. It made the world capable of complexity. Before it, Earth had oceans and life. Certainly, but life largely without bodies, without visible ambition, without the oxygen-rich sky that later worlds would take for granted. After it, the stage existed for animals, for movement, for sensory experience, for ecosystems built not just on chemistry, but on interaction. The Proterozoic did not create us directly. It created a world where creating us was no longer absurd. And perhaps the most humbling part is this: none of it was aiming toward us. Cyanobacteria did not fill the world with oxygen because they hoped for mammals. Ancient archaea did not host bacterial partners because they dreamed of forests. The first eukaryotes did not begin sexual recombination because they wanted eventually to produce symphonies and telescopes and sleepy people lying under blankets, listening to stories about deep time. Evolution has no such screenplay. Yet the chain holds. Accident, selection, persistence, catastrophe, cooperation, all of it linking forward until it reaches the modern room. That should not make us feel central. If anything, it should make us feel included. We are not the purpose of the story. We are one of its recent consequences. And that can be a very peaceful thought when you let it settle properly. The pressure eases. The demand to be everything eases. We belong to a process far older and larger than our immediate worries. The same Earth that learned to oxygenate its air, survive freezing, reconfigure continents, and coax complex cells into existence is still carrying us now. The ground beneath your home may include minerals first stabilized in that eon. The oxygen moving through your blood depends on ancient atmospheric revolutions. The mitochondria in your cells still perform a task that began as bacterial labor long before animals existed. Even the habit of cooperation, so fragile and so necessary in human life, has roots older than animals themselves. Cells learned it first. There is one more thing the Proterozoic offers, and I think it is especially kind. Perspective. Human time feels large from the inside. A decade can feel immense. A year can break you open. A single night of worry can feel endless. But the Proterozoic stretches those feelings into a different proportion. Not to diminish them cruelly, but to soften them. Here is an age where ice covered much of the planet and still life continued. Here is an age where oxygen poisoned old ecosystems and still life adapted. Here is an age where the world changed, not over days or generations, but across spans so wide the mind can barely cradle them. And still the story did not stop. Persistence is one of the oldest facts we know. That does not mean every form survives. Many do not. Most do not. The Ediacaran beings faded. Whole microbial worlds were overturned by oxygen. Climatic crises narrowed the living. But life as a process held. It rerouted. It changed style. It rebuilt from what remained. The Proterozoic, more than almost any other age, teaches that continuation does not always look like preservation. Sometimes survival means transformation so complete that what comes after would be unrecognizable to what came before. That is not always comforting. Perhaps but it is honest. And honesty can be soothing when it is spoken gently enough. If I could walk you one last time through this old world, we would begin on a shoreline of bare stone, under a sky only just learning to be blue. We would look out over waters once rich with iron, once dark with anoxia, then slowly changed by oxygen breathed out from invisible workers. We would pass through microbial cities layered in slime and chemistry. We would watch the first eukaryotic cells emerge from partnership. We would stand under the terrible white brilliance of Snowball Earth and wait, patiently, for volcanic breath to thaw the planet again. We would return to warmer seas where sex has entered inheritance and cells begin refusing to part. We would kneel by the seafloor while the first soft, strange bodies take shape. We would watch one small creature disturb the mat and know that the future has started to move. And then we would step back from the whole immense eon and see what it truly was. Not a prelude in the dismissive sense. Not a waiting room. Not an empty stretch before the real entertainment began. It was the forging of the conditions under which visible life could exist at all. It was the long, patient workshop of complexity. A world busy making some of the most important decisions in the history of the planet, just as your source script so beautifully implied. That work is still with you, in your cells, in your breath, in the rocks, in the air, in the fact that there are creatures now who can look back across billions of years and feel wonder instead of only confusion. So when you leave this old age in your mind and return fully to the present room, maybe carry one small piece of it with you. Not the cold exactly, though there was plenty of that. Not the rust, though that mattered too. Carry the patience. Carry the scale. Carry the quiet stubbornness of cells that changed the world without ever knowing they had done it. The Proterozoic was nearly half of Earth history. It was long, strange, mostly wordless, and astonishingly productive. It turned a raw planet into a world that could support bodies, ecosystems, and eventually awareness. It never needed spectacle to achieve that. It only needed time, chemistry, and life doing what life does best. Adapting, merging, enduring, trying again. And now here you are, at the far edge of that inheritance, warm and breathing in a room full of modern comforts, carrying inside you the memory of ancient bacteria, ancient ice, and sensius, ancient experiments in cooperation. Deep time is not somewhere else. It is built into you. The microbes were here first. The oxygen came slowly. The ice nearly won and did not. The cells learned to join. The bodies learned to form. The world learned to hold more life. And because it did, you can rest tonight on a planet that once looked nothing like home and yet was patiently, relentlessly becoming one. Let that settle over you now. The old seas, the rusting iron, the blue sky arriving molecule by molecule, the strange fronds on the seafloor, the first movements in mud, the long patient breath of continents shifting under ice and water and time. You do not need to hold all 2 billion years in your mind at once. Just hold the feeling that something vast and quiet worked for a very long time, and that you are one small living continuation of that work. That is enough. Good night.